Thanks, and welcome to my talk. My name is Ionut Balosin. I came from Wien, from Austria, and today it's actually talk about runtime optimizations in the perspective of two compilers, the one which is called C2, the traditional one, and the new one, the state-of-the-art one, which was recently added and inclusively developed in Java. So other things about me, I'm also a technical trainer. I conduct courses on the software architecture topics and also Java performance. I also write articles, mainly for the InfoQ, and also everything is published on my website, ionutbalosin.com. The presentation, the slides themselves, you can download them from my website, ionutbalosin.com/talks. And also I do conferences. I speak around the world to a lot of places. Today's content, we'll go through a few topics. We'll start with a bit of introduction to set you the context. Then we'll zoom inside the Scalar replacement, and I will tell you what Scalar replacement is. Also, we will touch the virtual calls, how both compiler optimizes the virtual calls. We talk about vectorization, loop optimizations, and then we will end up with some conclusions. Just before to start, I would like to remind you that the presentation is actually based on the article I wrote 1 month ago, and it's also published on my website. It's called JVM Just-in-Time Compiler Benchmark Reports, where I created a lot of benchmarks based on different optimization patterns, and I tested those two compilers, C2 versus Graal Just-in-Time. Few things about the configuration. Probably the one which is really worth it, it's the actual version. I use 12 on Linux, x64, and I use also not any commercial JVM implementation, but only free license. In particular, I used OpenJDK and GraalVM Community Edition. And to do these benchmarks, I use JVM version 1.21. And this is a big, big reminder. This talk, it's not about GraalVM Enterprise, which is a commercial JVM. So the optimizations that I will talk today might different in that machine or in others' machines. I'm talking mainly about open source and license-free JVMs. And if you might ask yourself, it is a fair comparison, is it apple-to-apple comparison? Well, it depends on the perspective, right? Because for the application and for the end user, yes, what you care is actually about performance and licensing cost. However, from the compiler and the internals, it's very much different. Those two compilers are implemented in very different ways. If I have to sum up a bit about Graal Just-in-Time Compiler, it is Java-based. It is still early stage. It was recently released, the first production-ready version, but it's still in the beginning. It's not a mature compiler. It targets a lot of JVM languages, static, dynamic, and also native languages, for example, C, C++, Rust. So it targets a zoo of such languages and has a modular design. Also, it offers you ahead of time flavor, so you can compile ahead and run it. In comparison, C2 is the traditional one. All our code in production was run against this C2, and the majority of our code in production still runs on C2. That's why it's still a matter of interest. It has a C++ implementation, it's mature, it's production ready, but the thing is it was always written to optimize and for the Java code in essence. And besides that, I think nowadays it reaches a local maximum of performance. And it's a bit less flexible. So for example, it's not well suitable to add new optimization patterns. That's why, for example, during the last releases, the biggest improvements in C2 were more in regards to vectorization and intrinsics, but no completely new optimization heuristics. Nevertheless, today the baseline for Graal it's still C2 because it needs to be better than C2. And what it really matters is the production code, right? Because we can do benchmarks which are good. The benchmark are the ground basis. However, the production code is what it really matters because in production we don't run benchmarks. Nevertheless, there are three main distinguishing factors for Graal just-in-time compiler. As I was telling you, it's a very much different than C2. However, they both run and tries to produce better optimizations for Java code. First one, it's called partial escape analysis. The second one is called improving lining, and the last one it's in regards to guarding optimization for speculative code. And let's see briefly what of this means. You have also the paper at the bottom, so you can download and read the full paper. However, the main idea for the partial escape analysis is it does the analysis for one object if it escapes on some branches. For example, you have an if-else branch. And if, for example, if the object escapes in only the called branch, for example, where the object is not taken, it doesn't make sense to allocate it anymore. And this optimization is called partial escape analysis. And it works not on the bytecode, but on the intermediate representation. And it is also effective in conjunction with other parts of the compiler, like for example, inlining, global value numbering, and constant folding. The next one is called improving lining or late inlining. For example, C2, the traditional compiler, does inlining for one method at a time. And it inlines first the trivial method, and bigger methods, they are inlined later in a greedy fashion, in a separate phase. However, on top of this, C2 inlines based on some thresholds which are not adjustable during the runtime. And this, it's not always beneficial because what most of the inlining approaches does, they actually assign a benefit for one call site, and when that benefit, when the budget is hit, the inlining doesn't happen anymore. However, in some cases, even if you reach the budget, it might be beneficial to still keep inlining, right? So this is why this new approach enables this adaptive inlining during the runtime. And on top of that, it doesn't enable only one call site, only one method at a time. It could inline a cluster of them, because inlining makes sense, especially where you have interprocedural analysis. It makes sense to inline multiple methods together. And the last one, it's called guard optimization for efficient handling. What happens, for example, both C2 and Graal does a lot of speculative optimizations during the runtime. The problem is, if one of that speculative optimization proved as being wrong, what it means, it gets back and it's de-optimized, and the compiler switches to the interpreter. And this bail off from compiler to the interpreter, it's not cheap. Because in essence, we need to switch from the compile, from the optimized code inside to the interpreter. And it means to create the interpreter state, to reconstruct the local variables, to reconstruct the operand stack. And on top of that, for example, during the runtime, if that speculative optimization triggers some objects that were allocated on the stack by the scalar replacement technique we'll discuss about them. So basically, if during the optimization some objects were not allocated anymore, when you switch back to the interpreter, they need to be allocated. And this kind of, in this paper, is specified an algorithm which actually measures the cost of an optimization when it is de-optimized back. So all of this, in my opinion, are the three main characteristics for like new heuristics added in Graal, which really makes a difference in comparison with the C2. And now let's go through some cases. The first one is called scalar replacement. But before understanding what is scalar replacement, let's zoom inside escape analysis. And what is escape analysis? Where every time when you allocate an object, it doesn't go into the heap all the times. And the analysis around that escapability, it's called escape analysis. It's actually assigns an object scope to each object created, and those scopes could be no escape. For example, if the object is really local and it doesn't escape and it's always visible to the current thread. The second one is argument escape, which actually means the object which is being created, it's passed to a method, but no other thread except the current one has access to it. And the last one is global escape, which means it could be accessible from other threads. So this is this process of analyzing the object scope. It's called escape analysis, and it is actually a phase for the optimizer which enables better optimizations, because if the scope is no escape, what could happen? Because it's local, it doesn't go and it is allocated on the heap, right? So in this optimization, it's called scalar replacement. So the optimization is called scalar replacement. However, the process which leads to this, it's called escape analysis. And now let's go through few cases and see how it is optimized under the hood. The first one, what I've did here, those annotations come from GMH, Java Micro Benchmark Harness. If you do micro benchmark profiling, it's the way to go. What I've did here, I've created in the no escape method, I've created a light wrapper. I allocated that and I return the sum of those fields. In reality, it doesn't make sense to create the light wrapper anymore, because it shouldn't go on the heap. It has the local scope, right? So that method should be equivalent to return F1 plus F2. The next case is when you have an object, but that object has an array in it. And in this case, it's called heavy wrapper, because besides F1 and F2, it has the array, which is the Z array. And inside the bold method, which is the benchmark method, I initialized, I create an instance, and then I return F1 plus F2 plus the length. So again, it doesn't make sense to allocate the object since it doesn't escape, because actually it should be equivalent to returning F1 plus F2 plus the length itself. So it's just the addition between these three. The third case is when you create an object, you have the wrapper object created, and based on the if-else, based on that conditional check, you decide if the wrapper is returned or not. So if the wrapper escapes the method itself. However, I tried to trick a bit the compiler, because in my case, object escapes was never matched because it was false. So only the second branch, the else branch, was taken. Actually, the wrapper, it was created, but it didn't escape. It never escapes out of that. And what could happen in this case, because it never escaped, it's still there is no sense to allocate it, because you create it based on the branch condition, it never escapes. And in this case, partial escape analysis helps a lot, because I was telling you before, partial escape analysis triggers this kind of analysis and decides if the object escapes or not based on some branches. And if the object doesn't escape, escape, which means it is always used in the called branch, it is not allocated anymore. And the last one, the fourth case, is in regards to passing an instance which is locally allocated, passing it as an argument to another method. For example, here I've created two objects, wrapper1 and wrapper2, and then I trigger the equals between those two objects. And if they are equal, return true, otherwise I return false, right? The problem here is wrapper1, because it is always local, it doesn't escape, so its scope is no escape. However, for the wrapper2, it depends actually, because if the method equals gets inlined, its scope becomes no escape because it's still local. However, if the inlining is explicitly disabled or it fails, right, so it escapes and its scope becomes argument escape. And having all of these four cases in mind, I run all of them, and these were the timings actually. The first one was for the no escape, so in both cases, both compiler triggered the same optimizations, and the average response time was around 2-3 nanoseconds per operation. However, in all the other cases, C1 and C2 was slower. And it was not like slightly slower, was about 1 order of magnitude. Which actually concludes that the Graal just-in-time compiler enables better optimization. So it is able actually to check not only if the object escapes, has no escape in the first phrase, however, due to the further decisions, further optimization, it is able to remove such allocations. In comparison, C1, C2, it's not able to do that. So in essence, if there is a condition which makes not clear from the compilation time if the object escapes or not, or if there is passed an argument and after that, during the runtime, the method gets in line, C1, C2 cannot trigger the optimization. So it cannot get rid of those allocations. And the last one, it's actually refers to the, by default, C1, C2 doesn't consider escapes, it doesn't escape arrays if their length is bigger than 64. And in my case, previously, the object length was 128. That's why. So this is actually something that you should consider if you have applications where you allocate local objects, but those objects are heavy objects, they contain arrays, but they don't escape. If the length is greater than 64, you end up with allocations on the heap. So basically, you need to tune that JVM parameter in a sense. The next category, it's about virtual calls. What is a virtual call? It's actually a call which could be overridden. And this is a bit of still theory to understand that the test cases that I triggered. Let's suppose you have a base class, for example, an abstract class, which has a method compute, and it has only one implementation, elg1. So CMat is the base class, and elg1 is the implementation. The problem is during the runtime there is seen only one target invocation for that compute, which belongs to the parent, to the base class. This is called monomorphic call side because it has only one target invocation during the runtime. But there are cases where there are two possible target invocations because the CMat, it's actually extended by elg1 and elg2. In this case, if during the runtime are seen two such target invocations, it becomes bimorphic. And starting with the third implementation, no matter what you have, 4, 5, 6, and so on, it is called a megamorphic call side. And why is this important? Let's get back and see what tests I did. I created a method which is called execute, which takes as an argument the cmath, actually the base class and an integer, and it calls the compute. Actually, when I call the compute, because I've tested it with different implementation from ELG1, 2, 3, 4 until 6, it becomes a megamorphic call site because there are more than 2 such possible target invocations. So every time when I've called that method, it actually dispatched to the appropriate implementation, which belongs to either ELG1, from ELG1 to ELG6, to the appropriate target invocation. And these are the benchmark tests. First, I tested with only one implementation, ELG1. It's the first upper benchmark. And what it does under the hood, it actually gets the parameter and multiplies it by 17, by a constant, doesn't matter. The bimorphic one, I've used 2 implementations of the base class, ELG1 and ELG2, and I did the sum of them, just to tell to the runtime, hey, there are 2 implementations for this. And the similar case for megamorphic 3, I decided to take 3 implementation of the base class, and I also continued my test cases with megamorphic 4, 5, 6. So each multiple implementations, the number belongs to each test case. And what are the figures around this? As you can see from the monomorphic is the top, bimorphic, and so on, until the last one, megamorphic 6, which means 6 possible target implementation. The timings were slower and slower with just-in-time C2. And the question is why? Because as you can see, for the monomorphic and bimorphic, the timings were almost there. Anyway, it's still 1 nanosecond. Right, so it's something very, very tiny. It may be not such much of interest. However, starting with the third possible implementation, there is a bigger difference. And let's see what happened under the hood for the bimorphic case, the case where you have 2 possible target invocations for the same call site. And this is assembly. Why I actually include the assembly? Because it's single way to prove what happens under the hood. Otherwise, you cannot. Without providing an evidence, it's still just a guess. Showing you a simplified version of the assembly code, it's relevant because it really gives you a clue of the optimizations that were triggered under the hood. So this is, let's start with C2, and let's start with the bimorphic case. And in this bimorphic case, recall, we had 2 possible target invocations. And in this case, what it does, both of them, as you can see, they are inlined, and there is the comparison to see if that instance belongs to ELG1, jumps to L0 label, and does that shift logic and addition. So this is actually the body of the compute method. If the instance is of type ELG2, right, jump there and do the multiplication. And if there is another possible third implementation which was never encountered during the runtime, it is added actually this uncommon trap. Because it might happen, for example, you dynamically load during the runtime some classes. And in this case, it is de-optimized. So this is how just-in-time compiler C2 handles such case. Graal, the next slide, it actually uses the same pattern. It checks if there is the instances of ELG1, does the same operations. If there is ELG2, jumps there to L0 label and does the multiplication. And for another possible implementation, it prevents you, for example, to run this code if you dynamically load another instance during the runtime. It still needs to be compatible, and in this case, it adds a de-optimization routine, so the last L2. In conclusion, by such case, where you have two possible target implementations, they are handled in similar ways by both compilers. So it's actually about inlining caching. Both body of those target methods were inline, and there are several jumps, several comparisons. And for another possible implementation, there are added either an uncommon trap in case of C2, either the optimization routine. However, this case with two target invocations was actually similar in both cases for both compilers, but let's see what happens when you have the megamorphic 3. So it's actually a call site which receives 3 possible target implementations. And this time, C2, what it does, as you can see, actually nothing. It just triggers a virtual call, so which means actually it doesn't proceed further with any optimization. It doesn't inline anything. It just triggers an invoked virtual call, which in essence it's costly because these virtual calls, the runtime needs to provide, proceed in the vtable to create a lookup, and based on that vtable lookup, the target it's received and so on. So there are extra operations that are handled during the runtime for these virtual calls. However, C2 doesn't produce any further optimization. In comparison, GraalJIT, what it does, it's similar principle to what it did before. If it is an algorithm of type 1, jumps there, it's inlined, as you can see. If it is algorithm of type 2, jumps there, it's still inlined. If it is of type 3, it's still inlined. And for the fourth possible implementation, or any other possible implementation, it adds that jump when it gets and de-optimizes and bails back to the interpreter. So in conclusion, the megamorphic 3 call sites for Graal optimizes them very nicely. However, just in time doesn't proceed during any further optimization. And there is a limitation in HotSpot in C2. It's called due to polluted profile context, which means in essence a method is used in different contexts with independent operand types. And this is actually the task raised since a while to fix this by enabling context-dependent split profiles. However, it's still in open. I don't think it will be tackled soon. Probably it's not a matter of interest, it's not something which really makes sense, but it's still a limitation in C2. The other cases like megamorphic 4, megamorphic 5, and megamorphic 6 are optimized in both compilers, by both compilers in the same way, by Graal and C2. C2 does the vtable lookup, triggers the virtual calls. However, Graal inlines and adds the inline caching with the comparison jumps. Next one, let's talk about vectorization and loop optimization. So until now we saw some, I would say, some strengths for Graal just-in-time compiler. Very nice optimization. Let's move on next and see what is in regards to vectorization and loop optimizations. But before really going into the benchmarks, really a bit of theory. Let's suppose you have to multiply for example, two arrays, and assign the result in C. So you have C equals B multiplied by A, right? You can do that in a Scalar version, which means one single instruction, one single pair of operands, one instruction, one data. Or you can do it in a vectorized version, the right case, where you can have the same instruction, which is the multiplication instruction, and multiple pairs of operands. operands or multiple data. And these vectorized versions are actually implemented via SIMD, or single instruction multiple data execution units. And during this talk, I will refer to two types of such SIMD extensions, which are in essence the SSE registers, XMM registers in this case, which are registers on 128 bits. So basically in this one XMM register, you can pack, for example, 4 floats, 2 doubles, and so on. And the next category is the so-called AVX, and in particular, I will refer to YMM register, which are actually double in comparison to XMM, which can store until 8 floats. So 8 floats could be packed in one register. Besides that, we have also auto-vectorization. What is auto-vectorization? It's actually an analysis for that compilers trigger during the runtime and decides if the serial code could be turned into a vectorized one. And based on that analysis, it triggers such SIMD instructions. However, a loop, to be able to be auto-vectorizable, it needs to fulfill some criteria. And the first criteria is to be a countable loop. What means a countable loop? It's actually this example. A countable loop needs to have a limit, which is loop invariant, and it needs to have a stride, which is known and constant at compile time. And only in this case, the loop, it's countable, and these countable loops are unrolled. Unrolling means actually the body of the loop, it's duplicated, and instead of doing one statement per loop cycle, you can do, for example, 8, because it enables also the instruction level parallelism. And besides this, the loop itself needs to have single entry, single exit. It needs to have straight lines. So for example, if you have a switch inside the loop, it's not valid for optimization. However, if with masking it's allowed, you have only the innermost loop, it's vectorized. So if you have nested loops, only the innermost one it is. And if you call another function, it might not be a possible candidate, however, for auto-vectorization. However, the intrinsics are allowed. Okay, so having all of this as a very, very basis for our next and first test case, let's zoom and let's see what it is about. Let's suppose I have to multiply 2 arrays, 2 float arrays, and the result I assign it to C. It's very simple, actually. What happens, this is the benchmark I've initialized. As you can see, it's quite a high length for each array, because I want to bypass at least the L1 CPU data cache. I want to be bigger than that. And then the benchmark method, what it has, it says C of I equals A of I multiplied by B of I. And the result I return in C, and that's it. If you have to measure this, you will see that Graal just-in-time compiler, it's way slower. And in order to understand why, and what happens, let's get back. And I will start with this representation, because I'll go through snapshots of assembly code, but I think it's important to have first the big picture. This is for the C2, sorry, just-in-time compiler. So this is actually the pattern how a vectorized loop looks like during the runtime when it is optimized. So initially we had, for example, we had this, just a very simple loop. However, due to the optimization that were triggered during the runtime, the loop is transformed into such complex structure. And the first one, it's called Scalar preloop. What means Scalar preloop? It's actually, it peels, in essence, the first statement, the body of the loop, outside of the loop, because it needs to pre-fill some caches, and also it's important for the data alignment. And then the vectorized main loop, what it has in it, it actually, per each loop cycle, it is able to multiply 32 floats for each loop cycle. Why is that? Because it uses YMM registers, right? So in one YMM register are packed 8 such floats, and for each loop cycle they are used for multiplication. So in total 4 multiplied by 8, so 32. And if the remaining, because there could be a remaining which is less than 32 but bigger than 8, it still continue with the third one, which is called vectorized post loop, which still does 8 by 8. And the last elements, which are less than 8 until it reaches the array size, they are triggered 1 by 1. So this is actually the pattern based on which that vectorization is actually handled. Auto-vectorization is handled during the runtime. And if I have now to go through each of these, how they look like, the Scalar pre-loop, actually I was telling you, it's actually the first incipient instructions which precede the main loop, and they are actually there for aligning, for memory aligning, and for data CPU pre-filling. And as you can see here, actually the first multiplication is outside. And then inside the main loop, you can see, they are anyway bolded, you can see the multiplications which uses YMM registers, and you can see the line which is still bold, add R13D20, which means per loop cycle there are 32 such multiplications of floats. So every loop cycle does 32, 32. And the pattern is actually written on the last line of the slide. Then, if there are still a remaining, which I was saying it's less than 32 but bigger than 8, it goes and does 8 by 8. You can see add R13D and 8. It does 8 at once per loop cycle. And for the remaining, it's 1 by 1 until it reaches the end. In comparison, Graal, just-in-time compiler, what it does loop peeling. It's the same theory, alignment and pre-filling of the CPU data caches. And here it's very simplified. Everything is in a scalar fashion, and it's 1 by 1. And the missing factors are, for example, there is no loop unrolling and there is no vectorization. And that's why, actually, you can now compare with the previous pattern and have a bit of understanding why such different in performance. Because Graal just-in-time doesn't enable these optimizations on this particular case. How it looks like, loop peeling, the same. It peels, actually, the loads, the first outside of the loop, and then inside the main Scalar loop, it does 1 by 1. You can see increment EDX 1 by 1 until it reaches the end. And the biggest conclusions out of this is C2, just-in-time compiler, I would say it really triggers wonderful optimizations. Because it uses YMM registers, it uses the vectorized shape, the synced instructions, and handles the remaining, of course, in a scalar fashion 1 by 1. However, Graal doesn't do that. It uses only the scalar and the shape and does 1 by 1. And just to, it's like a conclusion based on this test case. Vectorization is really a big missing core feature from OpenJDK and GraalVM CE. They don't have vectorization to my knowledge. So if you have a lot of mathematical or arithmetical operations, be very careful, because C2 is much better in this sense. And also loop unrolling, it was not triggered. Next one, it's a bit of corner case, but I think it's still very interesting. I kept the same code. What I changed only the type of the stride. So now the type of the stride is not int anymore, but it's long. Which means you can see the one in pink or red, it's long L equals 0. Before it was int I equals 0. And all the rest is the same. And in this case, you can see the performance is way slower. For example, for C1, C2, initially it was 57 microseconds per operation, and now it ended up with 253, for example. So the performance is way slower in this case. In comparison, Graal, it's not so big difference. Before it was 230 microseconds per operation. But what happens in this case? Why so slow? You just change the type of the stride from int to long. And if I have to put both in to compare side by side, the C2, how it looks like, the main loop, it's scalar and 1 by 1. And the same for Graal, it's still scalar and 1 by 1. So I would say in this particular case, both compilers were not able to proceed further with optimizations like unrolling, and the vectorization support it's missing here. And if you want to check what it happens actually inside the generated code, this is the one from C2. And as you can see, the main loop has that line which says add R13 and 1, so it's 1 by 1. And surprisingly, there is a Safepoint pool. Before we didn't have a Safepoint check. What is the Safepoint check? Actually, the Safepoint, those Safepoint checks are actually a way for the current thread to leverage the control to the VM for some specific operations. For example, like the optimizations, like class loading, stop the world pauses in general. So every thread from the JVM periodically, when they run the code, they have these checks, because if the check is proved, they park and let the VM to run some internal operations. And this is like a global state. And it was added here. The same case for the Graal. Actually, it's similar. It adds the Safepoint and adds 1 by 1. In conclusion, based on this specific example, multiplication of those two array elements with the long stride, it has one main scalar loop, no loop unrolling, no vectorization, and the Safepoint was added. So be very careful if you have loops with strides like long. The last case, it's about unpredictable branches. What I did here in this case, I was actually created an array, and each element of the array, it's actually initialized with random numbers before 0 and the threshold limit, and then I iterated through the array and I computed the sum of the elements only for those which have the value which is less than threshold over 2. And that's why it's unpredictable, because everything was random and there is no predictability in this pattern. So some could be bigger, some could be true branches, some could be invalidated. And in this case, I also included the baseline without any check. The predictable branch was actually the branch with all the numbers were, for example, lower than the threshold. And our case, it was unpredictable one, and in this case, Graal was way slower. What happened in this case? C2, what it does, loop peeling, the same scalar main loop with an unrolling loop factor of 8, so actually 8 such checks per loop cycle, and it ended up with the scalar post loop. So this is quickly what happens, loop peeling, the same rationale, it peels out the first one, and the scalar main loop, as you can see, are 8 such move instructions, and everything is checked in one loop cycle, and you can see add EDI comma 8, and the remaining one is 1 by 1 until it reaches the end. In comparison, Graal, what it does, peeling, and Scalar loop, which is done without any unrolling. This is the loop peeling, the first part of it, the same principles, and the Scalar version of the main loop, which is 1 by 1, but again without any unrolling. High-level conclusions out of this test: unpredictable branch. So C2 was better. Main loop was with an unrolling factor of 8. And of course, the post loop was 1 by 1. However, Graal didn't unroll the loop, so that's why it was way slower. In summary, I think this is very important if you have been asked about what's the difference, what is the current status between these two compilers. I think the optimizations like scalar replacement and virtual cores are way better implemented in Graal. Vectorization is really a core feature which is missing in Graal, but again, I'm talking only about OpenJDK/Graal CE. So mainly license-free. Loop unrolling, I couldn't find a case in my benchmark presented today where loop unrolling happened for Graal. And intrinsic support, I didn't touch them during the current presentation, but intrinsic support, it's better in C1, C2. And in my reference, I have a slide, another presentation when you can take details about these intrinsics. Gracias, and I hope you enjoyed the presentation. If you want to get the slides, there are the links and the article further in addition that I was mentioned about. Thanks a lot, and wish you a wonderful conference so far.
Thank you very much. There is no time for questions, but you can ask all the questions in the last time, okay?
Yes.
Thank you so much for the talk.
Thank you.